All right, this is the final lecture for Chapter 19, Aldehydes and Ketones. All right, so pretty sure we left off here. Predict the major products for each of the following. In the first reaction, we have 1-phenyl, 1-propanone reacting with ethyl magnesium bromide and then water. This is a Grignard reaction, so presumably there would also be diethyl ether here, and those make alcohol. So you're going to take this ethyl group, just put it as ET minus. It'll attack the carbonyl, kick off there. And so the product will be this here. All right, the added piece will be right there. We've got 1, 2, 3, 1, 2, 3. And so there's your product. In the second reaction, we have potassium cyanide and hydrogen cyanide. That is going to convert this carbonyl into a nitrile. So we're going to get, from the first step, the cyanohydrin right there. And then in the second step, with the lithium aluminum hydride and then ultimately water, those are going to convert the nitrile group into a reduced form, which ultimately is going to be an amine. And this is 1 carbon, so right there, and then NH2 will be your final product. In the third reaction, we have phenyl magnesium bromide and then water. So again, this is a Grignard reaction. It's going to convert that aldehyde into an alcohol. Because it's an aldehyde, you're going to get a secondary alcohol. I'm just going to shorthand it here. All right, so here's the 2 hydrogens. Those are the same. And so this would be diphenylmethanol as a product. Again, that's a secondary alcohol. Up here with the ketone in the Grignard reaction, we got a tertiary alcohol. And then the final reaction, this is going to be the Wittig reaction. And you're going to take this carbonyl and break that bond. You're going to break this here. And so this piece is going to attach right at the carbonyl there, essentially replacing the oxygen. So you're going to get the double bond just like we've got there or there. And then 1 and 2 other carbons. So 1 and 2, and there's your final product. All right, section 11, the Baeyer-Villiger oxidation of aldehydes and ketones. You're going to take the aldehyde or ketone, like right there. You're going to react it with a peroxy acid. So just to remind you, this looks like this. Those are peroxy acids, and then you're going to, by using that, convert the aldehyde or ketone into this ester. Notice the the carbon here is bonded twice to an oxygen, whereas in the product, it has 3 bonds to oxygens. And so that carbon is getting oxidized as a result of this reaction. You can see the mechanism of it here. We have the peroxy acid attacking the carbonyl, nucleophilic attack. The peroxy acid functions as a nucleophile and attacks the carbonyl group. And then you have a proton transfer that's intramolecular. So a proton is transferred from one location to another. This step can occur intramolecularly because it would involve a 5-membered transition state. We have 1, 2, 3, 4, 5. So it forms a cyclopentane type ring. Remember, those kind of look like envelopes, and those are pretty stable. Their bond angles are nearly 109. I think they're 108 degrees, actually, but it's pretty close to being the ideal tetrahedral angle. All right, so the carbonyl oxygen right there gets protonated. This oxygen will become neutral, resulting in this oxonium ion over here. The other oxygen remains negative, and then that'll go down and reform a carbonyl. And you'll see that this is going to be an alkyl shift, or it could be a hydride shift if the R group there represents a hydrogen. All right, and so the R group here moves over to that oxygen as a result of it, but the carbon-oxygen bond right there remains intact. Now you see, there's the carbon-oxygen bond, and now the R group is on the oxygen, and then the oxygen-oxygen bond breaks, and you get this carboxylic acid. Oxygen-oxygen single bonds are pretty weak, so this should not be surprising that ultimately is a bond that breaks. And then, again, you get your substrate converted into this ester. All right, we can use the Baeyer-Villiger oxidation of aldehydes and ketones to convert cyclic ketones into what we call lactones. These are just cyclic esters. So right here is the ester group. And so that ketone has been converted into a cyclic ester. We call those lactones. All right, so we have migratory aptitude here in the Baeyer-Villiger oxidation. The fastest to migrate or rearrange will be the hydrogen, followed by tertiary carbons, then secondary and benzene rings, I guess, or phenyl groups, and then primary carbons, and followed by the slowest to rearrange being the methyl groups in this particular type of rearrangement. So we have, in the top reaction, we have a methyl group versus this carbon there that's secondary, essentially, because look, we've got 1 and 2 other carbons there. We're going to ignore that carbon in this respect. Notice it doesn't have quaternary carbons as even a possibility because we're excluding the carbonyl there. So technically this methyl group would be a primary carbon, but for the sake of these reactions, we've got a secondary here and a methyl group there. So secondary are faster than methyl groups, so the oxygen is going to place itself in between there, and we get that product. For the bottom reaction, we have a hydrogen, which is the greatest for migratory aptitude, versus a benzene ring, and so the oxygen will place itself between the carbonyl and the hydrogen, making benzoic acid. All right, so predict the major product of each reaction below. So what we're going to do is, this will be for the Baeyer-Villiger oxidation. We've got this oxygen versus that oxygen. We've got 1 other carbon versus 2 other carbons. So we're going to say this is secondary, that's primary, and secondary are greater than primary. And so the oxygen is going to go in between there. So your major product would be that. For the middle reaction, we've got a hydrogen versus this carbon, and then that one is technically a secondary carbon versus a hydrogen, and hydrogens have the highest migratory aptitude, so the oxygen is going to place itself in between there. And create a carboxylic acid, like that. And then for the final reaction, we've got that carbon versus this carbon. We've got 1 and 2, so we make this a secondary group. and we've got 1, 2, and 3, so we have a tertiary group, and tertiary groups have a higher migratory aptitude than secondary. So we're going to get a lactone here. Actually, and I'm drawing this wrong because I was going for a 5-membered ring, but we're placing the oxygen in between there, so it goes from a 5-membered ring to a 6-membered ring. So there's the ketone, here's the oxygen, and then right there and right there. So if I number these, it would be 1, 2, 3, 4, 5 technically. And so the numbering here is actually going to be 1, 5, 4, 3, and 2. So 1 is no longer bonded to 2, but that just is what it is. And so there's your product. Section 12 is synthesis strategies. So here's some questions you should ask when doing problems here in this unit or this chapter. Is there any change in the carbon skeleton? Yes or no. Is there any change in the functional group? Yes or no. So here we have some examples of changing the carbon skeleton. So we are in the first type, forming a carbon-carbon bond. We could go from a ketone here, cyclic or not, but a ketone. And you're doing the Grignard reaction. That's going to form a carbon-carbon bond. Now we've got a ketone, so you're going to get a tertiary alcohol here as a product. If we react the ketone with potassium cyanide and hydrochloric acid, you'll get the cyanohydrin. Again, we formed that carbon-carbon bond like we formed that one over here. Or we could do the Wittig reaction to create this carbon-carbon double bond. And I realized I messed up here. That should be a 2, Roman numeral 2. Is there any change in the carbon skeleton? So here we have carbon-carbon bonds breaking. So again, this is going to be the Baeyer-Villiger reaction. We're comparing those two carbons. So we've got secondary versus methyl, and secondary has a higher migratory aptitude than methyl groups. So the oxygen gets placed in there, creating this major product. Now we have the carbons here and there, and those are no longer bonded to each other. We can split this off by adding some acid, and we'll learn this in the next chapter, that we could actually convert that ester into acetic acid ultimately. So we'd break this apart, and you'd also get isopropanol. So if you wanted to collect acetic acid, you could. If you wanted to get isopropanol, which is rubbing alcohol, you could do that by taking the ketone there, adding some peroxy acid, and then some acid here, and water will actually break that ester apart. But you don't need to know that reaction for this unit. So is there any change in the functional group? That's the second question. We have an alkyne going to an aldehyde. We've got an alkene going to an alkyne or an alkane. We've got an alcohol. We've got the alkyl halides. Look back at those chapters to see how to convert between those. It says over here, the reactions covered in this chapter, I guess they're meaning here aldehyde and ketone. So we've seen alkynes, we've seen alkenes, we've seen alkanes, we've seen alcohols, alkyl halides, and now we've got the aldehydes and ketones. And so there's a lot of stuff here. This would be, excluding the aromatic rings and pericyclic reactions, but we've also got those as, possibilities of things that can be done to molecules. So there's a lot that we're adding in this unit, a lot of different reactions here. But this is just showing you how wonderful organic chemistry is, how we can, in some ways, make anything we want because there's reactions that can interconvert between any of these functional groups. It might take multiple steps, but it can be done. All right, so here is a flow diagram or a flow chart showing many of these interconversions. Now the aldehydes and ketones one is limited to what we saw in previous chapters and how to make them. There is one reaction here of what they can do, but again, going through this chapter again, you'll see a lot more things that the aldehydes and ketones can do. All right, so here we have a table showing functional groups that you're trying to synthesize, in this case alcohols, from possible starting materials. So this is a retrosynthetic look at things. For example, we could take an alkene and convert it into an alcohol in two different ways. We could add acid to it to get the Markovnikov product. Or we could add borohydride or borane and THF to get the anti-Markovnikov product. My handwriting is sloppy there, I'm sorry. If we have an alkyl halide, we can react it with sodium hydroxide to get that alcohol. Ketones and aldehydes can be reduced. If you needed to go from a ketone, you could reduce it to a secondary alcohol. If you have an aldehyde, you'll get to a primary alcohol. If your desired product is a ketone or aldehyde, you could start with alkenes, alkynes, or alcohols in the ways shown here. If you have an alkene, you could use ozonolysis to give you this aldehyde. If this was substituted like that, then you would get a ketone. And the other product, by the way, would be acetone from this. If that was tri-substituted, then the product would be another aldehyde like this. But that's what you would get from ozonolysis. You could start with alkynes and water, sulfuric acid, and mercuric sulfate would give you the oxymercuration, demercuration to give you a ketone. If you're using an alkyl borohydride compound and water, hydrogen peroxide and then sodium hydroxide, there you'll get an anti-Markovnikov product that gives you this aldehyde. If you have an alcohol to start with, you could oxidize it using the chromic acid solution. If your desired end product is a carboxylic acid, you could start with an alkyne. With this terminal alkyne, you get, from ozonolysis, you get a carboxylic acid. Notice up here, this was an alkene in ozonolysis, which gave a ketone. If it's an alkyne, you'll get the carboxylic acid. If you have an alcohol, you could oxidize that. Notice this is a primary alcohol. This was secondary. The secondary alcohol gave the ketone. The primary alcohol actually goes through two oxidation steps, one to an aldehyde, and then the second step would go to this carboxylic acid. All right, now we have this ketone here and all the different ways that it can be used. We have the geminal diols on the top left. We have the acetal in number 2 there. We've got the cyclic acetal in 3, which we can use to make alcohols protected, or ketones protected, I should say. That's a protecting group. In 4, we've got the cyclic thioacetal, which can be another way to reduce a ketone into this alkyl group. We've got the ketone going to the imine in number 6, the enamine in number 7, the oxime in number 8, the hydrazone in 9. We've got an alcohol in 11. That one's secondary, a tertiary alcohol in 12, so that's the Grignard reaction. The cyanohydrin in 13. You could use the Wittig reaction in 14 to convert it to an alkene. And then finally with a peroxy acid to an ester, you convert the ketone to an ester in number 15. Section 13 is spectroscopic analysis of aldehydes and ketones. So here's just some information that you should, I don't want to say memorize, but maybe do your best to try to memorize it. But you have in cyclohexanone, the carbon-oxygen bond, the double bond has a peak at 1715, whereas one that's got conjugation with it is 1680, so a little bit lower frequency. And then you have the comparison here between cyclohexanone, cyclopentanone, and cyclobutanone. You see the number is increasing as it gets smaller, meaning it takes more energy to vibrate that bond, giving you different peaks. All right, now keep in mind these wonky looking pictures going forward are just because I took pictures of a textbook and had put them in there. I hadn't updated the PDF on Canvas for you yet, but it's still functional enough to see the numbers and everything. So you have the nitrile bond, the CN triple bond, the carbon-carbon triple bond, carbon-carbon double, carbon-nitrogen double, benzene, carbon-oxygen double, and so on, and where their peaks typically are, the intensity of the peak. Remember, like if it's an intense peak, then it's going to go way down. If it's a medium peak, it might be like this. If it's a weak peak, it'll be down like that. All right, and then luckily you get all these different examples of types of bonds and where they're going to show up in IR. This is why when I found these, I had to put them in something because it is, in my opinion, very useful, especially because we're seeing different functional groups. We have the alkane, we have an alkene, an alkyne, alkyl halide, alcohol, ketone, aldehyde, carboxylic acid, ester, acid anhydride, amides, acid chlorides, benzene and benzyl, and then amines. So you could memorize it from there. We have this IR spectrum of some random, oh, it's not random. Okay, so this is 1, 2, 3, 4, 5. That's pentanal. And you're going to see that there's a medium moderate intensity peak at 2719 and another moderate one at 2830. The key thing for aldehydes is the carbonyl one is at 1726. But you're getting at 2830, you've got the groups over here showing up, and then at 2719 is where you're getting that peak. Actually, I should clarify, all of this is like the alkyl group, and then you have the CH bond, you have the CO bond. All right, so for HNMR, we've got all these different types of hydrogens to look at. We've got the methyl one at 0.9, methylene, those are CH2s at 1.3, methine, which is CH at 1.4, methyl ketones, the orange highlighted ones are the hydrogens they're looking at here, and so on and so forth. So in this chapter, we have aldehydes, we have the ketone, so again, 2.1, and you should also see, if it's a ketone, again, 2.1. If it's an aldehyde, it'll be between 9 and 10. Again, these are actually the same functional groups as earlier, so you can see where the hydrogens are showing up for these types of functional groups. All right, here we have coupling constants and stuff like that. Not so much a big deal. It's not something I would focus on a test, but if you were a chemist, you might need to know like why you get extra splitting and why two things are so close to each other. HNMR spectrum here, we have some alkyl group at 1.2 and 2.1 for that methyl ketone. And then at the bottom, we have this, what is that, 1, 2, 3 carbons. So that would be 3-phenyl propanal. Okay, and so the aldehyde hydrogen is always going to be between 9 and 10. We've got these two hydrogens here. We've got these two hydrogens there. All right, so we have the methyl one next to the carbonyl. So again, that should be around 2. But then it's also, somewhat close to that benzene ring. So it's being extra deshielded by the benzene ring. These two here are also being deshielded. These two hydrogens have 1 and 2 neighbors, so they should be a triplet. And likewise, these two hydrogens have 1 and 2 neighbors, so should be a triplet. And we see over at the right, we have 2 triplets, and they're each around 3. So their integrations and their splitting would be the same. They're technically slightly different. I would say that, like, which peak is which? Well, first of all, we have the benzene aromatic ones. It does say its integration is to 5, and there's the 5. We have the 1 hydrogen over here. The others are 2 triplets. So which is which? Well, the hydrogens near the carbonyl group should be deshielded a little bit more. So I would assume those are that one. And then the one next to the benzene ring, these are the ones, I should say, would be the ones a little bit upfield, just because the benzene ring doesn't deshield quite as much as a carbonyl is. All right, so for carbon-13 spectra, we have from 0 to 200 ppms. All right, you can see alkanes at the far right, carbonyls around 200. They have hybridization and what they're showing up as in these peaks. Excuse me. Aldehydes and ketones, both of those greater than 200 or around 200. Again, same functional groups, just the different values for their peaks in the C13 NMR. And here we go. We have a molecule. This would be 2-butanone or just butanone. It has a peak at 209.1. It might be very small, but it's there. Then you've got 1, 2, and 3 other carbons. These two would probably be the next 2 far downfield. This would be the most upfield, and we see those 3 peaks there. So at the very least, from the NMR, you're getting a carbonyl carbon and then 3 alkyl carbons. And that's what you get. You would pair up a C13 with an H NMR, and you should be able to figure out the spectra from that. You also would compare the IR to all this. You should see the carbonyl peak at like 16 to 1700, a pretty strong one. And again, that would verify that this is definitely a carbonyl. All right, and that is it for Chapter 19. All right, you have a test coming up next week during lab on just this chapter. Make sure you are prepared for that. On Tuesday, we'll start Chapter 20. Same with Thursday, we'll be going on Chapter 20. So just make sure you understand that those will not be in the next test. Take care. Have a good weekend.